Hi, this is Dr. Goldstein, and today we'll be talking about factoring polynomials. So first, let's talk about why we might want to factor a polynomial very briefly. And one of the main reasons why we might want to factor is that we want to find roots. So what this means is we find real numbers C such that when we plug them into a function, we get 0. That's what I mean by a root. So there's two main methods that you probably already know for factoring. And the first one is called reverse FOIL. And this works very, very well with degree 2 polynomials. And this is specifically reversing the process of multiplying two binomial terms together. So for example, if I take the polynomial f of x equals 3x squared plus 2x minus 1, I can reverse FOIL it as 3x minus 1 times x plus 1. And this is simply recognizing that when I take the first terms and multiply them, I get 3x squared. When I take the outside and inside terms and multiply them and add them, I get 2x. And that when I take the last terms and multiply them, I get negative 1. Now, when I look at this and I ask myself, where is this equal to 0 if I want to find roots, I see that that means that 3x minus 1 has to be 0, so x has to be 1/3, or x plus 1 has to be 0, so x has to be minus 1. And the last thing that I'll leave you with this method, and this is a bit of a teaser for later, is that we can write f of x as 3 times x minus 1/3 times x plus 1. If I distribute that 3 to that x minus 1/3, I get the 3x minus 1. So the thing to note here is that if x equals c is a root, then x minus c is a linear factor. So we had that x equals 1/3 was a root, and so x minus 1/3 was a factor. X equals negative 1 was a root, and so x minus a negative 1, so x plus 1 was a factor. Okay, another method that you may have seen for factoring is grouping. This works particularly well with, you can use it with degree 2 polynomials. You can also use it with degree 3 polynomials where reverse FOILing won't work. So for example, if I take f of x equals x cubed minus 3x squared minus x plus 3, I can take the first two terms and factor out an x squared, and I'm left with x minus 3. And then the second two terms, I can, the third and fourth term, I can factor out a negative, and then I'm left with x minus 3 there. And now the reason why this method works is because in both of these terms now, I have an x minus 3. And so I factor that out, and I'm left with x squared minus 1. And then I notice that in this second factor here, I have a difference of squares, and so I can factor that as x minus 1 and x plus 1. And so here we note that x equals 3, 1, and minus 1 are roots. And so we have the three factors, x minus 3, x minus 1, and x plus 1. These are factors. Okay, so there's a big question. These methods work really well for degree 2 and degree 3 polynomials, but what do we do with higher degree polynomials? What do we do with higher degree polynomials? And one thing that I'll say at the outset to this is that this is a really hard problem. This is a really hard thing to do. So I'm going to show you a theorem that helps with this, but the bottom line is that this is just a really, really, really hard thing to do, and there are no methods that work all the time for every single polynomial, and that is mathematically provable. But here's a theorem that works a lot of the time. It can help a bunch. It's called the integer root theorem. And what this theorem says is if we have a polynomial that you see here in green, f of x equals a sub n x to the n plus a n minus 1 x to the n minus 1 plus etc. So the a's are the coefficients, and then we have the various powers of x. If this is a polynomial function such that each of these coefficients ai is an integer and the last term a0 is non-zero, so our constant term can't be 0, what this theorem tells us is that every integer root, so every root that is a whole number of f, is going to be either a positive or a negative divisor of this constant term a0. So we said that a0 couldn't be 0, our constant term couldn't be 0, so it has divisors. Now if we look at the last two examples that we did, our constant term here is minus 1, so a0 is minus 1, and so this has divisors, either 1 or minus 1. These are the whole numbers that divide that integer. And we want either the positive or the negative ones. If we look at the second example that we did, it was f of x equals x cubed minus 3x squared minus x plus 3. Here, the constant term is 3, and so the divisors are 1 and minus 1, and also 3 and minus 3. And what this theorem tells us is that these are potential integer roots. If there are roots that are integers, they have to come from this list. And if you remember the work that we did earlier in this video, it turns out that the first polynomial here has roots minus 1 and 1/3, and so minus 1 ends up being an actual root, and then there's a rational root, so it's not an integer. And then in the second example that we did, the roots were 1, minus 1, and 3. But negative 1, oh, I circled the wrong ones. Hang on, let me go back and do that. Oh, I wrote the wrong ones there. My goodness, why didn't you tell me? Haha, just kidding. The roots were 1, minus 1, and 3. Negative 3 was not a root. Okay, so let's look at one more example. How would we actually use this theorem to find the roots of a polynomial? This will help us factor. Maybe if we want to find the roots, this just answers how do we find the roots of these things in general. So let's look at this polynomial, f of x equals 2x cubed plus 2x squared minus 8x minus 8. So if we want to factor this polynomial, really the first thing that we should do is actually factor this 2 out. So when you're factoring, always remember to try the easy things first. Okay, so now if we look at this polynomial, this semi-factor polynomial, and I look at x cubed plus x squared minus 4x minus 4, my constant term for this polynomial inside the parentheses is minus 4, and so the divisors are plus or minus 1, plus or minus 2, and plus or minus 4. And so what we can do to check if these are roots, so remember, things are roots if when you plug them in, you get 0. We actually plug these in. So if we plug 1 in to our polynomial, so if I do evaluate f of 1, so I have 2 times 1 cubed plus 2 times 1 squared minus 8 times 1 minus 8, this actually evaluates to minus 12, so it's not a root. When I plug in minus 1, so again I'm evaluating 2 times minus 1 cubed plus 2 times minus 1 squared minus 8 times minus 1 minus 8. This comes out to 0. So x equals minus 1 is a root. And then if I plug in 2, I get a root. Oops, I changed colors. If I plug in 2, I get a root. And if I plug in minus 2, I also get a root. So in both of these cases, so here x equals 2 is a root, and here x equals minus 2 is a root. And at this point, I stop because I have found 3 roots, x equals minus 1, x equals 2, and x equals minus 2. The degree of my polynomial that we started with was 3, and I know that I can't have more roots than degree. So I can stop because I cannot have more roots than the degree of my polynomial. So I've found all 3 roots of this polynomial. If my goal was to factor this polynomial, now I know what the linear factors are. So if I wanted to factor and not just find the roots, we already pulled that 2 out. So I know that I have 2. And then remember what we said before. Anytime I have a root, I know what a linear factor is. So my root x equals minus 1 gives me the linear factor x minus negative 1. The root x equals 2 gives me the factor x minus 2. And the root x equals negative 2 gives me the linear factor x minus negative 2. So again, this comes from x equals negative 1, x equals 2, and x equals negative 2. And so I know, I'll simplify this, I know that my polynomial factors as 2 times x plus 1 times x minus 2 times x plus 2. So if I wanted to factor my polynomial, there I've done it by finding all 3 roots. So this is a very good example of using the integer root theorem where it tells us, here are all of your roots. And in a later video, we are going to see, well, what do I do if I can only find 1 root or 2 roots, but I know that there might be more? So we'll address that question later. But for now, this is just getting started using the integer root theorem.